Now we're going to talk a little bit about displaying information using graphs. So displaying information using graphs is a way to convey to people what we've learned about data by investigating it and collecting it, collating it, organizing it, and displaying it so that they can have a better understanding of the data. Give you an example. There are 5 people in my family, right? So that 5 people, we're going to use blue to represent the boys and red to represent the girl. There's only one. So if I use a pie chart, then 4/5 of that is going to be boy. 1/5 of that is going to be my wife, the only girl. Well, we do have a girl dog, but I'm only counting people here. So that percentage, 20% of our family is female, and the 80% is male. So that's how you use a pie chart to graphically display the information about data. Again, this would work for any size of a sample that you wanted to use. Sometimes it can be very helpful when you look at pie charts that help you determine what's the most likely thing. So if you were to knock on the door, what would you expect, male or female, to open the door? You'd probably expect male because there's 4 out of 5 of that group who are male. So that would help you to know what to expect. That's a pie chart. Let's move on to bar graphs. Bar graphs are a similar way to represent data, but they have a different style. So they use an X and a Y axis. So in this sense, we just used the entirety of the circle to represent our family, the population of our family. Now what we would do is we would say, I don't know, if I asked a bunch of kindergartners, what's your favorite fruit? Then I might get a bunch of different answers. Let's say I asked my kids' class what was their favorite fruit? And 5 of them said strawberries. Strawberries are delicious, good fruit for you. So there'd be 5, right? Here's the y-axis, 0, 1, 2, 3, 4, and 5. So 5, you'd put a bar there, and that would represent that 5 kids said blueberries were their favorite fruit. However, 3 kids said blueberries. 1, 2, 3. So I would have a different bar that represents not the strawberries with the 5, but the blueberries there. Turns out there's some other kids. These other 2 kids loved blackberries. So 1, 2. See how these bars are different? What they represent in that they're separate from each other, which will be different from histograms we'll see the bars are collapsed on each other. This gap represents that the type of data we're dealing with here is a categorical data. Categorical data, like strawberries, are just as much of a fruit as blueberries and just as much of a fruit as blackberries, but they are different fruits. So they have a categorical variable, a nominal variable, and all we can do is count frequencies, how many of these we saw in the data. One person said that brown berries were their favorite. I don't think there's such a thing as brown berries, but I had this marker and it seems brown, so brown berries. All right, so that's our bar chart. It's how we graph out data. And you can also see a trend here for which is the most popular. If you were going to pick the type of fruit we should order for picnic, for the kindergartner's picnic, you could clearly see that brown berries was the least, so you probably shouldn't pick any brown berries for the picnic. You should probably include strawberries and blueberries, and if you need a third one, go with the blackberries. Does that make sense? You've got your bar chart. It helps you visualize the data, and then you have more information by seeing the trend in that data, and you can make decisions based on that will hopefully make good decisions based on the data. That's a bar chart. So now we've gone through pie charts, bar charts, and next one we'll do, after I erase all this, Sorry, brown berries. The next one we'll do is histograms. Histograms have the same setup as a bar chart, except we're using now ratio data. So that means that 0 on the x-axis means that none of it's there. And that as we continue going up, that each one is at interval scale so that those bars actually collapse on one another. If we said I did a bar chart showing, I don't know, how many people scored well on the exam, right? Also, I'll say, okay, so here's they scored 0. Here's they scored 20, 40, 60, 80, and 100. So we could have a histogram showing how many people in the class. Here's 0 people. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I use this histogram, now look, 0 to 20, I didn't have any people that scored 0 to 20, but I did have a couple people who scored 40. No, not exactly 40. As you see here, this scale is just in chunks of 20, but that 40 could represent everything from 30 to 50. Similarly, the 60 should represent everything from 50 to 70. So they cover the interval of that. So if I have this, then I'll say that there was 5 people that scored for that, there was 10 people that scored 80 to 90, and there was 5 people who scored 100%. What this does is it creates for us, sorry, I got this. There, it's better. That's a little bit better. So now you can see this bar chart on the vertical axis is showing you how many people scored that, the frequency of occurrences in the population that we saw, and on this x-axis you're seeing which scores on that variable happened. Also, it can show you the trend of how did the class do overall, right? This gives you a description of the class. I would say, wow, what a great job, class. The vast majority of you were up in this section where you really understood this, and very few of you didn't understand this material well enough to pass this test. That could give me a sense of how well did I cover that material on the exam. If, let's say we found a bar chart for my class's scores on a test, and it looked like this, then I would know I'd done something wrong. Something happened here where I didn't present this in an accessible way, and so that gives me sense of the descriptive statistic telling me, hey, it's time for change. It's time to go into the inferential mode and really figure out what are the differences, what are the things that you could implement that would shift the graph in another way. If I saw this, then I would say, perhaps I'm not really pushing the edge here with my stat students, or maybe I'm the greatest professor of all time, right? That's what you would initially think. And then if you think more critically about it, you'll say, well, what might be the issue here? It might be that I'm not pushing the edge enough and that they could grow more, or just that they did a fantastic job. Sometimes that happens. You get groups that are just 100% engaged and ready and do the work. And so maybe that's one of those times. But all these information, all this visual display of information helps us to know, to give us a sense or a gauge of our efficacy. And that's what I like to see, is I like to see something up like this, and then I could up the amount that I'm delivering. I can make the class more engaging and cover more materials. If I saw the bottom part, then I would say, ooh, I've got to change the way I'm addressing something. It again might be me, or it might be the students. It might be a context issue that's different. If you've taken Psych 300, you know about the fundamental attribution error. But when all you have is the variable to change as yourself, you tend to look at this and say, well, I didn't make this class hard enough, or I made this too hard, or I made it just the right amount hard, if you have that sort of nice distribution in the middle. Whereas the reality might be, this class was totally prepared, that class was totally unprepared, and this group had both a mix of prepared and unprepared. might not be you, but you have only you to change the variable for, so you should take that perspective to see if you are the person or the problem in a scenario where the data shows you that there's a problem, or if you're even the solution, or if you're even the part that's good. That's a helpful and a beneficial thing to look at data and understand what impact you're making on it. So that is histograms. Now, the book goes through this tremendous amount of mathematical effort to figure out how to get you guys to find equal intervals, right? That everything's going to have an equal interval when you display it. If you're interested in reading about that, by all means, go ahead. I'm not interested in testing you on how to create equal intervals for a histogram category. Really, what I need you to know is that a histogram is basically a frequency table, as we've covered before, laid down on its side and represented in these bars. The bars collapse together because they're ratio scale. So 1 is next to 2 because that's equidistant from 7 to 8. It's not a bar graph. Bar graphs have those bars separated from each other because it's categorical data that's represented in bar graphs. Again, both bar graphs and histograms in the vertical axis, the y-axis, are saying a frequency count, right? How many people scored this particular score on that variable. Yeah, it's weird doing this. Because it's like I would be looking at you and saying, is this really easy for you, or did I not explain this well enough? You know, one of the things to note is that if you've been reading ahead in the book, all of this is going to be reviewed to you, or at least most of it. I mean, there's some things I'm adding in here, but if you've read in the book, you should be right with me, because the book does a great job of explaining this. Later, we'll get to the book where the book's wrong, and I'll have to explain why it's wrong, and understand that where it's wrong, we need to know why it's wrong, and then what to do about that. Oh, one last thing. I'll talk about rounding. I'll talk about rounding later. Don't worry about it. How about that? Do not worry about rounding and significant figures. 2 decimal places and round up everything. That's the gist of it. But we'll talk about more of the why we're going to do that. And one last part that the book talks about is something called a frequency polygon. Basically, it's just a line graph. And this is a different way to represent data. Looks like a mountain range. You've seen that before. Instead of having bars, it just puts a dot where the bar would be, right? So I'm sorry, this would be like this. And then this bar would be like this. It's just a different way of representing the data. And you might like that, you might not. I tend not to like line graphs, but maybe you do. And there's reasons for it. If you have different types of data that you're displaying, you might want to show that nuance via the line graph rather than the bars that are in a histogram and in a bar graph. There's also stem and leaf diagrams, which basically are frequency tables, frequency distributions. The shapes of distributions we'll get to when we talk about the normal curve. But basically there's normal, bell-shaped, there's rectangular shaped, there's U-shaped, there's inverse U-shaped or cone-shaped, there's J-shaped, there's positive skews and negative skews. We'll cover all that when we do normal curve. That's chapter 3. First, we have to go to chapter 2, where we're going to learn about measures of central tendency and variability. Okay, we're going to be dealing with mean, median, and mode. These are all our measures of central tendency. Measures of central tendency basically means that you're looking at the gist, or how do we summarize the group with one score. And you might ask yourself, well, why do we need to summarize a group with one score? And the answer is really because you can't keep of all that data in your mind at once. If I said to you, I have 3 boys, they're 12, 9, and 7 years old. That's easy enough for your brain to keep in your mind. But if I said to you, my nieces and nephews are 18, 15, 13, 11, 9, 7, and 5, and 3, and not 1 yet. You probably can't keep all that information. There's 10 of them. I have 10 of them. I also have 2 nieces on the other side. And if I keep adding numbers to that, the ages of my nephews and nieces, you'd get confused by. And you wouldn't be able to hold it all in your mind. So if I use a measure of central tendency, you're able to think about that entire group of people, that sample of people, and understand what's the gist or the summary or the middle point or the most frequent. Those are our measures of central tendencies: the average, the middle point, and the most frequent. And that's where we get mean, median, and mode. We're going to start off with the mode. Not a la mode, although I'd love some ice cream right now. Mode is the most frequent number in a data set. This can be used for categorical data too, because you can count up frequencies of, say, if I said, how many of you are wearing sandals, Havaianas or Flojos or what are those? I got some over there. Oh, Quicksilver. I got Quicksilver sandals. We said, what type of sandal do you have? Mine are flip-flops. Some of you have the strappy kind. We all have sandals, not all of us, but most of us, and so there are different types of that. And if we did a modal search for that, we would find that there'd be like 10 people who had the Old Navy kind. I have some of those too. $2 at Old Navy. They were great. They lasted several years. But that would be the most frequent one, right? If there was 10 of those and everybody else had like, one of this kind or one of that kind, the one that's the most frequent, even if it's a categorical one, that's called the modal. If we have, say, a distribution of scores, and the book uses the distribution of scores, and it says, here's this data set. It says, how many dreams do students have in a week? And so it measured these 10 people, and it said that they had I hate it when these things don't work. Seven, 8, 8, 7, 3, 1, 6, 9, 3, and 8. So, as you can see, there's variability here. That means that they're not all the same score. But also, if we wanted to find out, okay, if there's a college student out there, we want to use this data to describe to them what's the most frequent number of dreams a student has in a week, then we would find that 8 is represented thrice. So the 3 times that we have 8 represented, that is more frequent than any other score that we see. Although 9's represented once, 1's represented once, 6 is represented once, 3 happens twice, and 7 happens twice. So now we have multiple iterations of numbers, 7 and 7, 3 and 3, but we have 3 of 8s. So 8 becomes the mode. So the most frequent score in our data set here is 8. Now, these are very active dreaming people. I don't think people dream that much, but whatever, this is made up data. As much of the data that we'll explore in this class is all made up. The issue with making up the data is, rather than use real data, which would give you insight into real people, there's some issues of ethics or confidentiality with regard to using real data about people. So the book makes up data, and I'll make up data, and you'll make up data. Because what you're actually learning is the process by which we determine this particular mode. You're not learning about student dreams. But you can imagine if there was really a study, if somebody really was spending all their hard research time on finding out about how many dreams college students have, this might be something that they would do, and they might represent and tell people, hey, the modal dreams for students was 8. That is the most frequent thing that we saw in our data set. So that's a mode. Super easy. Remember, I told you already, this class starts out incredibly easy, and it develops from there to get more and more complex. Understandable, but it's going to take more cognitive effort for you to understand. This is very easy. My 7-year-old, he's upstairs right now. I could bring him down here and say, which one's the mode? The mode's the one that you see the most frequently. And he'd be like, well, there's 3 8s, so I think it's 8. That's not the issue here. The issue is that why would we do that is we would use categorical, or when we're using categorical variables, remember those are the ones that differ only in name, they're nominal, then we would use this. I'm using an example of the numeric version here just to demonstrate that it could also be shown in a numeric variable. I hope that's enough mode for you. I think I'll ask you one question about the mode on one exam and we'll be done with it. Why? Because it's easy to understand, and so I think you got it. And secondly, because we don't use it often. It's not something that you're going to see a lot of modal presentations. There is something else about the mode that you should know. Oftentimes people will talk about a bimodal distribution. Okay? What's a bimodal distribution? Imagine that we didn't have 10 in our set, we had 11. And now I have 3. So now there's not 1 3, not 2 3s, but there are 3 3s, as well as 3 8s. That would be called a bimodal distribution, and we would say 3 and 8 are the mode. 3 and 8 are the mode. It is a bi meaning 2, modal distribution. Unimodal distributions mean there's only one, and that's what we'll see when we go to the normal curve. Bimodal distribution, I'll give you an example of that. So oftentimes, you know, we looked at the scores on histograms, like what normal scores would be like on my exams for the demonstration of a histogram. Often what actually happens on my exams is that I get a bimodal distribution. I'm back. Bimodal distributions is often what I see. So again, this would be the percentage of people who get a certain score, and then this would be their score, you know, 0 to 100% on an exam. Usually what you'll see is that if I plot it out, it looks kind of like this. So that what ends up happening is, there are 2 modes. It doesn't have to be exactly the same number of people that get them, but what we see is that there's 2 sections. This is a group of people that clearly didn't understand what we were talking about this portion of the class and didn't do the work, or a combination thereof, or maybe I screwed up presenting it. This is the group of people that did the work and understood it and got the right information. But you see, it's basically a bimodal distribution, so that there's very few people on the center who got kind of the average amount. Most people got all of it or very little of it. And that's called bimodal distribution. So that is the mode. All right, the next one on our docket is median. I'm going to write it right here in the middle. I'm going to write the median right in the middle because that's what it is. The median is the middle score. In fact, you've heard of median before. This is driving down the freeway and somebody says, watch out, there's an accident, they've pulled over to the median. And if you're driving down the freeway, you know that the median is going to be in the center. It's the middle. It's not on the off the edge on the side. It's the middle. So the median is the middle. And in numeric data, that's exactly what we have. So let's use that same data set that we had before. The 7, 8, 8, 7, 3, 1, 6, 9, 3, 8. But I'm just going to do something to that data. To find the median, you have to start with either the biggest or the lowest number, and you have to go through that numerically. So we're going to use the numerical sort of numbering, right? Lowest to highest. That's as simple as I put it. Oftentimes when students screw up a median on a test, they take the data as was presented, right? So I just presented that data, 7, 8, 8, 7, 3, 1, 9, or 7, 3, 1, 6, 9, 3, 8. I'm going to take that data now and I'm going to start with the lowest number, which was 1. So here's 1. And then we had 2 3s, if you remember that. And then we had 1 6. We had 2 7s. We had 3 8s. And we had 1 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good, I've gotten it correct. I did a little check there to make sure that I hadn't forgotten any of the numbers because, well, it's easy to forget numbers, and if you do simple checks like that, like count to say, did I get all those numbers? Because I know there are 10 numbers. We tested 10 students, we asked 10 students how many dreams they had in a week. Then I'm pretty sure I've made a good check that I've gotten all of them in here. All right, I'm gonna bring you guys in a little bit closer. All right, there we go. So these numbers, we have 1, 3, 3, 6, 7, 7, 8, 8, 8, 9. And we have to determine, well, what's the middle number? And we've put them in ascending order from the least to the greatest. So there are 10 numbers here. Do you remember I also altered that number last time to see what would happen if it was bimodal? We'll do that here in a second. But for this one with 10 numbers, we're just going to count to the middle. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So right here in between these two is the median, or 7. If you have an odd number, right? If you have an odd number, then you take the two middle scores, 7 plus 7, 14, and you divide that by 2. 7. Pretty simple stuff, right? Again, it's not going to be the same way all the time. You might have a different distribution that has a different look to it. So I'll give you a different distribution where it's an even number of scores, and then you have to add the two numbers up and figure out Here's a new example. This one looks like the old one, but it's different. Now what do? We're going to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These two are our middle numbers. So now we're going to take 6 plus 7. 6 plus 7 is 13. And we're going to divide that by 2. Does anybody know what that is? 6.5. So now 6.5 will be our median. So now you know how to calculate a median. What is a median? It's the middle score. What does that mean? It means that half of the scores in a distribution, this distribution is just our data sample or whatever you want to call it. It's just a group of numbers together. Half of the scores in this distribution are less than that number, and half of this distribution are scores that are more than that number. That's what the median is. What do you do if you have an odd number of scores? 1, 3, 5, 7, 9, that's your distribution. Well, you just count to the middle one. That is your median. 1, 3, 5, 7, 9. 5 is a score that half the numbers are below and half the numbers are above. Not really, because you see there's an odd number here. So 5, conceptually you would split it into 2, an upper and a lower limit of it. And then the lower limit would go on this side and the upper limit would go on that side, and the same amount of scores are on that side as on that side. Remember, the same amount is important for median. So there's the same number of scores. Here we go. So 1, half of 1, 2, 3, half of 1, 2, 3. So the middle score, 5, means it's the median. If there's an odd number of scores, the median is the middle score. If there's an even number of scores, like we did in the two examples before, you take the two middle numbers, average them, add them up and divide by 2. That gives you the median for that distribution. So median. Where do you guys hear of median? When is median used? Well, median's used when a mean is a poor choice for describing data. That often happens when there are outliers in the data. We'll cover that later once we cover what a mean is and what it does, because the median is often used if there are extreme outliers. So if there's 1 or 2 scores that are vastly different from all the other scores in the distribution, then using a mean is going to really skew the average, and it won't describe to you what the central tendency of that sample is. A median would be a far better one because it's not susceptible to outliers. Where do you hear about median being used? Often you'll hear about it as median salary or median household price, right? So there are these things like, let's say you're out home shopping today and you wanted to know, well, what's the average home price? A smart realtor will tell you, well, we don't like to calculate average house price because that includes every single house that's sold, and there was a $13 million mansion that just sold. So if we said average house price right now, that 13 million is going to get included into the average, and then it's going to skew that data up. Or you might say that there was a really, really cheap house sold and it's a barely livable structure. It's just shack on a postage stamp of, rural county, but it counts as an actual house that was sold that sold for $20,000. That's going to reduce the price dramatically when we include that sale into the average home price. So instead of doing those, the 13 million or the 20,000, what we're going to do is we're going to say, well, what's the house price that half the people paid less for their house than that and half the people paid more for their house than that? That's better information for somebody when you have skewed data to sort of say, what can I expect? If you know that the distribution of things like, say, home prices or salaries is skewed, then you'd want to use a median. For example, you can go on not covered California, that's the insurance one. Transparent California, the SACB does salaries, right? You can look up my salary, you can look up everybody who works for the state's salary. And if you look up who earns the most, there are several people that are earning millions of dollars a year. I remember it was the head basketball coach for UCLA the last time I looked. He was earning something like $5-6 million a year. Now, obviously, head basketball coaches at storied programs like that command a high salary. Most state workers don't command that high of a salary. So if you look up, if you're like, well, what's the average state worker make? Knowing what the average state worker makes isn't going to make good sense for if you're going to go work for the state. You live somewhere near Sacramento, you might work for the state. It's a good job, good pension, stable job, good work environment. You're doing something good for the greatest state in the nation. But you shouldn't calculate in the highest paid person's salary into what you expect because that's going to skew the data. And you shouldn't calculate what the lowest paid person for the state is because you don't know, or is that an equivalent full-time worker? So what we should do is say, well, what's the average? And then we'll compare that to what's the median. And we'll see what the average is in a second when we do the mean. But the median is for those distributions that have big skews or big outliers in them to give us a sense of what we would expect. What would the average person expect? The median doesn't take into account this giant outlier in the data, just like the mean will. And the mean will be skewed and won't be a good measure of central tendency to use if we know that there are outliers in the data. Oftentimes people do use the mean when there are outliers in the data, and that can be a misuse of it, right? If you're trying to make a sense of it, right? There's the classic quote that I like to use. It's on our syllabi. Torture numbers and they'll tell you anything you want. You can torture numbers to say, well, look at this average. If you knew that the data was skewed and the mean was skewed in a direction to make the point you wanted to make, you could include the mean and everybody would be like, oh, it's the mean of that distribution. But it's more complex than that. You have to be careful about which measure of central tendency to use because you want to describe the gist of the data with these numbers, but you also don't want to describe data that people can't rely upon to make their decisions. So that's the mode and the median. The next will be the mean.